Everyone, this is a lecture about uniform circular motion. This will be mainly about understanding how uniform circular motion works and definitions, and calculate simple parameters for a uniform circular motion such as period, frequency, speed, and so on. Uniform circular motion is when an object is moving around a circle with a constant speed. A car taking a turn is an example. McQueen doing a loop-to-loop is an example of uniform circular motion. Assuming the speed is constant around the circle. Ferris wheel, generally we have uniform circular motion. And when you're going on a loop-to-loop in a roller coaster, you are doing a uniform circular motion. It's an interesting motion. It's a circular, around circle, but it's a kind of a 2D motion, but I can assume I'm along this line here to make it a bit simple. So I have a velocity v that is constantly changing its direction. So what we say here, something really kind of new and important, is that speed is constant. Uniform means constant, right? However, velocity is not constant. It keeps changing its direction, like you see in here. And since there's change in velocity, there's an acceleration. And acceleration, remember, was equal to, let me go to my pens here. Change in velocity over change in time, delta v over delta t still holds here. Acceleration will be in the same direction as change in velocity. This little figure here is nicely shown. If I take a velocity 1 and then the next one, add them as subtract them, take the negative of the next one. We're doing vector subtraction here. I can get delta v. That would be v final minus v initial, or v2 minus v1. And that would give me the direction of acceleration. We want to play around with this a lot, other than understanding conceptually that we have an acceleration because velocity keeps changing direction. It's here and there as you move, keeps changing direction. And because of that, there's always an acceleration perpendicular to the velocity at any point you consider along the circle. So we have always an acceleration that is towards the center. Keep that in mind. This figure is also nicely showing that. So speed is constant. That's the magnitude of velocity. Which is the magnitude of velocity. All right, that's the speed. But the velocity is not constant. It keeps changing direction. That could be something hard to understand in the beginning. Definitions. One definition we will have is how much time does it take to go around the circle once? So let's say I'm starting from here, going around the circle once. That is called a period. Here's the description of it. The time interval it takes an object to go around a circle one time is called a period. Another definition is, if I look at my watch and watch a circular motion, it will be circulating, going around and around and around. How many times it can turn, if it can complete a one full circle in 1 second. And that is called the frequency of rotation. It's something we quite often hear in daily life. And here is the formal definition of it. The number of revolutions per second is called the frequency. And frequency and period are related with this simple relation. Frequency is equal to 1 over the period, or I can rewrite this. These guys can switch. Remember my shortcut algebra. So I can also write the period. I'm going to use blue here actually. The period is equal to 1 over frequency. So if I know one, I know the other. Frequency is the revolution per unit time. Period is how much time it takes for one revolution. So the unit of t, the period, would be second. Notice we always use capital T for period, and we will stick with that. Remember, we were using delta t for time change, or small t for time. For period, we'll be using capital T. For frequency, we'll be using small f. And thus the unit of frequency will be 1/2 from here. We also call the second to -1, or as it listed here, hertz. Let me actually not confuse you here. This is also equal to hertz. So that's period and frequency. Period is how much time it takes for one full rotation. Frequency is how many times the object rotates in 1 second. We already talked about the velocity and acceleration, right? Velocity here, acceleration is always towards the center. There is this relation between velocity and acceleration. Acceleration is equal to velocity squared over r, r here being the radius of our circle. It's shown in here. I can also show it in there. That's my r, or there. The distance from center to an edge, that's what r is in a circle. So here is my r here, and here is my r. I can also find velocity period and velocity frequency relations. Notice again that speed was constant, so the magnitude of velocity is constant. Thus, I can apply the uniform motion equation, which is this equation here. The speed, let me say, velocity is change in direction. The speed is equal to delta x over delta t. Again, it's the magnitude of velocity. And if I look at one full rotation, what happens during that is the object starts from one point, goes and comes back to there. The distance it travels is equal to the circumference of this circle. And here's how we find the circumference, 2 pi r. So my delta x will be this guy here. And the time it takes for one full rotation was period. We already described that, so I'll replace my delta t, change in time, with period. And this will give me a relation between the velocity and the period. Again, if I'm not putting an arrow on a vector, remember velocity is a vector. If I'm defining a vector without an arrow, that means it's this magnitude. Actually, saying speed here would be an easy, more correct saying, but keep in mind I'm looking at the magnitude of velocity here. Direction always changes, and whenever I drop the vector sign, here I have the vector, here I have the magnitude. Then I'm looking at the magnitude. Another way I can call it speed. So velocity, a period relation here. And from there, I can solve for period. If I know velocity and radius, I can solve for period, 2 pi r over v. R, again, here is the radius. And v is the velocity. All right. Units, we know velocity unit, meters per second. Radius units will be meter, should be meter if I'm using SI units, and then my period will be second. These are very important definitions for a uniform circular motion. Here is a question. A car is turning a tight corner at a constant speed. Speed is constant. If we are turning a corner, velocity will be changing, right? So a bit later, velocity's direction will change, but speed is still constant. And the velocity will always be tangent to the circular line we are traveling. All right. So constant speed, we have a uniform circular motion. That's my clue there. And a constant speed, turning a corner, clues. That means I have a uniform circular motion. Okay. These two clues tells me that I have a uniform circular motion. All right, the velocity vector for the car points to the east at the instant shown. As we see here, what is the direction of the acceleration? Well, that's a simple matter after I learned what is in the previous page. Acceleration is always perpendicular to the speed, that's one thing, and always directed towards the center of circle. So if I come here, curvature might not be given and the center might not be given, but I can guess this car is going around a circle that has center somewhere around here. That means the acceleration should be in that direction. So it will be south. I can also guess it from the fact that acceleration should be perpendicular to my velocity at any point that I draw. So there we go. That's our acceleration, and our answers would be south. Here is a question involving all the parameters we learned about as uniform circular motion. We're talking about a saw blade here, and we all know that saw blade turns, right, rotates, and cuts something, and as it cuts something, it has a change in velocity. Its velocity changes direction. Let me draw actually two here. So if I draw velocity here, it will be like that. Assuming it's rotated in this fashion, and a bit later it will be changing direction and so on. And because of that, it will have, let's show the velocity here, change in direction. Speed is constant. They rotate at constant speed, and because of change in direction of velocity, we will have an acceleration that is always towards the center. Center would be somewhere here approximately, and perpendicular to our velocity vector at any point. So that would be my acceleration. What else did I learn? I learned that it will have a period which is equal to time for one full rotation. So if I pick a point at anywhere on the circle, let's say I pick this point and watch it go, it goes around, and it comes back to the same point as I start, watch that point. That's one period. And we also learned about frequency, right? It's revolution per unit time, but I'll say per second because we'll always use second as unit time, but it could also be per minute and so on. So how many times it rotates each second, that's our frequency. Units were velocity, again meters per second. I know most of you are all on board with this now, but some of you may not be. So let's review. Acceleration, meters per second squared. The period should be second, and frequency is 1/2. One more relation I learned is that frequency is equal to 1/period, and period is equal to 1/frequency. One more relation, acceleration is equal to v squared over r. All right, let's also add these. We also looked at another equation relating velocity to t, 2 pi r over t. And r here would be, I'll try it approximately, maybe this much to the center, the radius of the circle. This would be our blade here. Now I'm gonna read the question. This was my review for whatever we've learned so far. Actually, I want to add one more thing here. From here, since we know t is equal to 1 over f, right? From there, we know that we can replace this in here, and we can rewrite velocity relation with frequency as well. It will be 2 pi rf. So all these equations are important here. This guy, that guy, this equation, the relation between velocity and period, and relation between velocity and frequency. Now I'm going back to my question here. The circular blade of a table saw is 25 centimeters in diameter. Okay, I am given the diameter. I'm going to stop here. 25 centimeters, but I know I always use the radius. So I'm going to directly take half of that to avoid errors. I'm going to take that radius, and that will be half of that, 12.5 centimeters. I'm going to go even further, divide that by 100 to convert to meters, because I always use SI unit. I also know that I am a good physics student. I follow everything in the class. So diameter to radius, I took that right away to avoid errors. Let me rewrite that. And then I convert to meters, right? SI units will stick with that. That's what we have decided to avoid errors and make our job easier. Now I'll keep reading. 25 centimeter in diameter and spins at 3600 RPM. RPM here is revolution per minute. So that would be our frequency. 3600 RPM. I would call this a revolution per minute or rotation per minute. Now, this is frequency given in revolution per minute or rotation per minute. I am going to convert it to second. I'm going to write this. Again, I'm converting to SI right away. I want second. I don't want minute. So I'm going to say frequency is equal to 3600 revolution per minute. And if I convert minute to second here, let me do it your way. I have to say that's times 1 minute over 60 seconds, right? So I can cancel these minutes. So I'm going to divide. Let me actually delete that second here. All right. When I do that, I'm going to find my frequency to be 60. 60 revolution per second. That's actually 60 second to minus 1. Revolution is not a unit, so it's 1 over second. Or hertz. All right, hertz. All right, I know frequency, I know radius. How much time it requires for 1 revolution? What is that? Time for 1 revolution is the period. That's one question. 2, how fast is one of the teeth at the edge of the blade moving? At the edge, assume this is the teeth I'm interested in here. How fast it is moving. That's the velocity at that point, or we're going to find the magnitude or speed at that point. And what is the tooth's acceleration? All right, so we're going to find all these. First one is easy. I know this. The period is equal to 1 over frequency, and that's it. That will be 1 over 60 seconds to minus 1, and I'm going to find this as second. Once I do that, I'm going to find about 0.017 seconds. Then I'm going to find the velocity using that, because I know a relation between the velocity and the period. Or I can also use this because I also know frequency, 2 pi RF. And two of these equations should give me the same result. Alright, once I input all the numbers, I'll put 2 pi. R I calculated here, remember, at 0.125. Minutes, not minutes, meters. I got lost here for a second. And divided by the period, 0.017 seconds. And once I do that, I should get a value of 47.12 meters per second. So now I got my speed too. Once I have my speed and I know my radius already, I can find my acceleration. It's v squared over r. So I'm going to input my v from here. 47.12 meters per second. I'm going to square that guy and divide it by r, 0.125 meters. And that should give me an acceleration of about 1.77 times 10 to 4 meters per second squared. And this is fast. Now, does it make sense? That's about 1.8. We can round it to. Does it make sense? This is really, really large acceleration. And if you have ever seen a table saw, you would know that they really rotate fast, and they that gives them a strong force. All right, these are the properties of uniform circular motion. We'll look at some more questions, and I'll let you go after that. For example, here. An ice hockey puck is tied by a string to a stake in the ice. The puck is then swung in a circle. What force is producing the centripetal acceleration of the puck? Here we have a clue. We know that it's doing the puck is doing uniform circular motion here, and it has an acceleration towards the center, and its velocity would be perpendicular to that acceleration or tangential to the circle at any point. Notice anywhere along the circle we also have an acceleration towards the circle, and it's always perpendicular to the velocity. So here is my acceleration towards the center, and my velocity perpendicular to the acceleration. Magnitude is constant, but direction is always changing. Now the question is talking about centripetal acceleration. This acceleration is called centripetal. Let me not draw the arrow so you guys will think it's something different. This acceleration is called centripetal because it's towards the center always. So because of a secant center, it's kind of called centripetal acceleration or center secant acceleration. It says what force is producing that acceleration, and the clue here is that since there's an acceleration, there should be a net force in that direction, and something always has to provide that net force. In this case, that net force would be provided by the tension, right? There's nothing else there. It's on the ice. There's no friction on the ice, or very little, ignorable. So that would be the tension in the string. And that would be my answer here. I'm going to call it tension maybe. Again, my arrow. Let's put here tension. Usually we use T for tension, but maybe I won't because now we have a period as capital T. And that would be my answer here. A coin is rotated on a turntable. It moves without sliding. That means there is a friction there. At instant shown in the figure, which arrow gives the direction of the coin's velocity? Instant shown, we have the coin is actually here. So let me try to draw the circle the coin would take. It's kind of a little bit of inward. And at any moment along that circle, our velocity is tangential to that circle. All right? It will always be that. If it was here, this would be my velocity. If it was there, and so on. You got the idea. So at the moment it's shown, the velocity is along A. How about the acceleration? It would be along D, right? Because it's always towards the center. How about the force? Force is always along the acceleration, the net force we're talking about here. All right? But the question is asking us which arrow shows the coin's velocity. That would be A. I want to tell you one more thing we move away from this question is that here the force that causes this acceleration and helps the puck stay in its place would be static friction force, if it was asked. And it would be also towards the center, always towards the center. So whichever direction I have on my A, net force will be in that direction. And in this case, it will be static friction force. This is an extra thing I'm given, thinking from the previous question if it was asked what force would generate that acceleration. So there's always a force if there's an acceleration. But to this question, coin's velocity at the shown point would be, answer to this question would be A. Oh, it's actually asking that too. I forgot about this question. Which arrow gives the direction of the frictional force? We already described it, right? It would be this. Again, my puck is going along the circle. And there is an acceleration and force towards the center. This force is also called centripetal, actually. Center secant, because it's also always towards the center. And it would be the frictional force. All right, and towards the center. Two more questions here. One, engineer designs curves on roads. We go along that curve. Sometimes we have dips along the roads we're going, right? They also design dips and peaks in the roads, the segments of circles with a radius that depends on the expected speed and other factors. The car is moving at a constant speed and goes into a dip in the road. Going around a circle, constant speed, we have uniform circular motion. From now on, that's what we're going to think right away. Uniform circular motion. Whenever we hear going around a circle with a constant speed, and we will know that the velocity actually changes direction, but its magnitude doesn't change. So here would be my velocity, and so on. And here, let me draw one more. And we can imagine that as we are going into this dip, that would be our velocity. At the very bottom of the dip, is the normal force of the road on the car greater than, less than, or equal to car's weight? This is a very nice review of applications of Newton's laws, actually. We know that in a uniform circular motion, there is always an acceleration towards the center of the circle. Imagine the circle here. Here I have a total acceleration. Okay, my circle is not very good, but you guys got the idea. Since there is an acceleration in that direction, remember there is an F net in that direction. F net. And whichever direction we have F net, the forces in that direction are larger. Non-equilibrium. So if I look at the forces, I have normal force up, and I have mg down, or weight force down on this car, and mg will be smaller than the normal force. Well, I didn't draw them smaller, but here we have them. Why? Because we have an A in this direction, we have an F net in this direction. Let's write it down. The forces in the direction of A are always larger. Okay. This one is a similar question. This one is asking us, there is a segment, a segment of a road as a car is taken. This is like going around a curve, different than the previous one, not a dip or a bump. What force provides the necessary centripetal acceleration? We're taking a turn again. We have a radius, imagine a circle here, right? And there will be an acceleration towards the center. Let me use a different color here. Velocity is green in this one, so I'm going to use this. Always perpendicular to velocity towards the center, centripetal, center seeking acceleration. There should be a force keeping this car in here because it wants to go in the other direction. That's one logical idea here. Or if there's an acceleration in this direction, there should be an F net. And there's only static friction force. And that would be our F net here. Alright, generating that acceleration. And this figure here shows it. The static friction force is the force keeping the car in its place as it does its circular motion and causing this acceleration. Again, this force can also be called centripetal force. It's also the same as acceleration, always towards the center. Another quick question here. A hollow tube lies flat on a table. A ball is shot through it, circular. It does a uniform circular motion. As it leaves from here, which direction will it go? The only reason that this ball stays here because there is a force applied to it from this wall here, and that would be a normal force, and that's everywhere. That force causes it to do a uniform circular motion. All right, I'm going to call it Fn, or we call it also n here. Thus, there will be an acceleration towards that. That's the case for uniform circular motion, right? Always towards centripetal acceleration. How about as this guy lives? There's nothing pushing it towards that anymore, so it will take a straight line. Whatever its velocity here, it will go directly with that. It can't do it here because there's a push in this direction. It can't do it there, right? Its velocity would be that there, and so on. But after this point, it's left alone free, so it will go along this path. So C will be the path it follows. That's all I'm going to tell you for now. Definitions and conceptual understanding of uniform circular motion, and we'll do some more examples in class. See you in class.